Hi. In this screencast, I want to talk to you about a concept of center of mass. So we've talked around it this year, but it's time we tackle it head on because it's a really important concept in physics. And one, it's not that hard to understand at a qualitative level, but being quantitative about it can be a little bit challenging. So let's get started here. Okay, so the center of mass, which we abbreviate with COM in caps. Okay, so the center of mass, it's a way of referring to an object as though it was a point mass. So it's basically if I take the mean position of all the mass of the object, I can simplify it down and say I'm going to treat the object as though it was this one point of mass, a geometric point, that whose position I can know, and I can use that for solving momentum, energy, things like that. Okay, so it takes a complex distribution of matter and condenses it down to one simple, easy to work with point. Okay, so it's pretty straightforward, and usually in AP Physics, the problems they're going to give you involve objects that are rectangular, geometrically simple to work with, right? So if I got a a cube, a rectangle, a cylinder, a sphere, the geometric center of the object is pretty easy to understand, and that's where the center of mass is going to be. Okay, as long as there's an even density distribution, which there will be in AP Physics 1. But sometimes I do have to figure out where the center of mass is, and they rarely ask you this on the AP test, but it's worth learning. Okay, it's not that hard. So basically, to find the center of mass of an object, you're going to basically use what's called a weighted average, where I'm going to take the mass and position of each of the objects in my system. I'm going to sum up their mass times positions and then divide by the sum of their masses. Okay, so let's just see how this looks. Right now, you're like, what? Okay, but we're going to figure this out. Okay, so let's look at this. I have two objects here. All right, so it could be a star and a planet, whatever. I got, but in this case, it's a 5 kilogram object and a 2 kilogram object. Their centers are 3 meters away from each other, and I want to know what is the center mass of this two object system. So, here's what you do: you have to measure center of mass from some origin, like from some starting position, right? And you get to choose what that is. I could put it over here. I could put it over here. But I'm going to put it right here just to make my life a little bit easier at the center of the 5 kilogram object. So if I do that, I'm going to say the center of mass of this object system, its location relative to this point I'm starting with is going to be found this way. I'm going to say 5 kilograms times zero because its center mass is 0 centimeters away from that, plus 2 kilograms of matter whose center is positioned 3 meters away. So 2 times 3 divided by the sum of the two masses, 5 plus 2. And when I say 5 times 0 plus 2 times 3 divided by 7, I get this value here, 0.587 meters. So that means is the center mass of this system is located right about here. That's worth noting. If I was able to somehow hang this from a string, it would balance right here. We'll get to that in a later lesson. Okay. This is more of a typical thing that you would get on an AP test, okay? And they do ask this question sometimes. Okay, so I have an 80 kilogram uh, uh, cube that is placed on a 40 kilogram board. The board is 3 meters long. The 80 kilogram cube is half a meter across. So I want to know where is the center of mass with respect to the left edge of this board. Okay, so I'm going to make this my origin. So I'm going to say I have 80 kilograms, but where do I say it is? Like it's spread out between here and here. Well, I'm going to say it's a geometric object, so its center is going to be the center. So it's going to be basically 0.25 meters away from this edge. So I'm going to say 80 times 0.25. That's where that's where this one is located. And I'm going to say plus 40 kilograms, and its center of mass is located 1.5 meters away. So I'm going to say 40 times 1.5. And I'm going to divide by the combined masses. And when I do that, I get 0.67 meters, which means the center mass of the system is located 0.67 meters away from the left edge here. Now, why do we bring this up in this unit in particular? And that's because the conservation of momentum tells us something very interesting, which is the center of mass of a system cannot change its velocity unless there is some external force acting on the system. Internal forces may change the position of velocity of individual objects within the system, but not the center of mass of the system itself. It will remain where it is, or at least moving at the initial speed that it was moving. So you cannot, again, I must emphasize this, it's such an important concept in this unit. You cannot change the velocity of the center of mass of a system by using internal forces. When two objects in a system exert a force on each other, they in no way change the motion of the center of mass of the system. So let's see how this works out. And I apologize, it's a little bit tricky to do, but let's just try work with me here, okay? I'm trying, okay? Here you go. So let's just say if I find the center mass of this system here, so so I'm going to say this is initially at rest, okay? So here's what I've got. I've got a 2 kilogram object here, and I've got a 4 kilogram object here. So the center of this object is 10 meters away from this arbitrary point here. So I'm going to say 2 times 10 plus, this is a 4 kilogram object whose center is 12 meters away. So 4 times 12 over the combined mass. That gives me a center mass of the system is located here, 11.3 meters away from this point here. Now, here's what I'm going to do with it. I'm going to have an explosion. It's going to apply an equal amount of force in both directions. Okay, so 80 Newton acts for 0.1 seconds. That means it makes an impulse of 4. So that means each object is going to change its momentum by 4. So this object was pushed this way. I'm sorry, by 8. 8, yeah, okay. 8 times 0.1 is not 4. 8 times 0.1 is 8. Okay, so I'm pushing this one here and giving it 8 units of momentum in that direction. So since its mass is 2, its velocity is going to be 4 because it went from having 0 momentum to -8. This one got pushed in the positive direction, so it has to end up with positive 8 units of momentum. So that means 4 times 2 is positive 8. Now, 1 second later, let's see where the center mass of the system is. So 1 second after this interaction happened, this is traveling 4 meters per second for 1 second. So it traveled 4 meters towards this origin point. So instead of being 10 meters away, it's now 6 meters away. This object was initially 12 meters away, but for 1 second, it's been traveling 2 meters per second the other way. So it will go another 2 meters. It's now 14 meters away. Let's just check in and see where the center mass of the system is. Well, so now I have is 2 times 6 plus 4 times 14 divided by the sum of 2 plus 4. I get the same thing. It's so cool. The center mass of the system did not move because it was initially at rest, so it's still at rest. And those internal forces in no way were able to change the velocity of that center of mass. It's pretty cool. Well, let's have a center mass that's not initially at rest. A little bit trickier and a little bit harder for me to get explained here, but I'm going to give it a try. Okay, so now the easiest thing to say is this. Look, if this combined object is traveling at 2 meters per second, then the center mass of the system is traveling at 2 meters per second. And no internal forces between those two objects can possibly change that velocity. That center of mass will continue to travel at 2 meters per second. So if the AP Physics test writer say, okay, now after 2 seconds this interaction happens, where's the center mass of the system 8 seconds later? Well, I would just say, well, it's traveling 2 meters per second. If it did for 8 seconds, it traveled 16 meters. You don't even have to worry about the individual motions if you're only asked about the center mass. But I still want to show it to you here. So let's just try this here. Okay, ready? So everything's the same. I start off with the same two masses. I start off with the center mass at 11.3 like it was before. But here's the difference. At this point, it's now moving 2 meters per second. So at this moment, its center mass was here, but it's moving 2 meters per second. So it's going to keep moving 2 meters per second, as you're going to see. So at this moment, bang, I have that 80 Newton force acts for 0.1 seconds. So it's going to make 8 units of momentum change in the negative direction for this object here. So this one was going, it was 2 times 2 forward. So now it's 2 times 2 backwards. That's a change of 8. This one was 4 times 2 forward. Now it's 4 times 4 forward. That's a change of 8 in the right direction. Okay. So they do this for 1 second. Now, 1 second later, where would this be? Well, it was this one here at the time of the explosion was here, was 10 meters away. Now it's moving 2 meters per second this way. For 1 second, it's going to be 8 meters away. This one was 12 meters away when the explosion happened. It was, and so basically it's now moving 4 meters per second. So if 4 meters per second times 1 second is going to go 4 meters this way. So 12 plus 4 is 16. So that's where these objects are going to be as a result of this explosion. Now let's calculate where the center of mass of the system is. So now I have 2 kilograms, that's 8 meters away, plus 4 kilograms, that's 16 meters away, divided by the sum of their masses, I get 13.33, which is interesting because that's 2 meters farther away than it was here. And the system's moving 2 meters per second, so 1 second later, it should be 2 meters farther away. Boom. Okay, it's just the coolest thing. All right, but honestly, you almost never have to do it at that level. You just have to understand that internal forces cannot change the motion of the center of mass of a system. Thanks for watching.